As a start, I want to show a result from a survey which we have been doing at year-end 22. And so it's still rather fresh. What we have been asking is one question, that is, what are the short-term and mid-term challenges which different industries would face? And the response was rather surprising in a way that this topic of competence ranks highest. And you see the distance is also quite high. It's almost a 20 percentage point. People could give 3 priorities, so that is why the sum of all these dots is more than 100%. Now, with this risk of insufficient competence, we have several impacts. One is that we have direct impact on innovation. I mean, not enough people means we will also scale down on innovation, but also unable to manage complexity, unable to do what is necessary for quality, and that in the end will have impact on cost, which means, for instance, you have rework. In other words, we see a direct relationship in competence on quality, and that means on the other side, and this is why I showed that chart, that we need in testing additional competence, not in terms of number of people, because that we don't get, but in terms of how can we more intelligently test. And that's getting more and more relevant now because testing is currently changing very much. Some people argue, especially students that I know from university, that testing is boring. And I never saw it that way, but it could be because, I mean, as a student, you would like to develop code, and running code, of course, seems to be fascinating. Now, getting a product into industry scale needs verification and validation. And we are currently in a situation where we do on the code level, with unit tests, a lot of activities. We do some activities with respect to validation and integration and system level. But what we see with many clients, test strategy is mostly poor. That means not enough traceability, not enough clear perspective of how much regression test is necessary, and what is most dangerous, blind spots. And a blind spot, especially when it comes to cybersecurity, can be extremely dangerous, because if you haven't verified or validated a certain port or code segment or service, can be very sure that this will be sooner or later an entry for attacks. In other words, testing matters, and intelligent testing is the call of the day, because we lack the competence in terms of people. And so we have to improve the quality of our testing. I will in this webinar show some strategies, and especially 3 powerful methods from different abstraction levels, covering code analysis, moving onwards into fuzzing, that is a kind of a brute force test method, and gray box penetration tests. So 3 very different security verification and validation methods, which help to grow intelligent testing and therefore also beef up your own testing activities. Now, the motivation behind all that is product liability. That is, as a producer, we are held accountable for the quality of the product which we get into the market. The yardstick is very simple. Any released standard, any applicable standard, this is considered best practice. This is what is expected if you bring the product to the market. And that means also that we look very much into the different standards with respect to security, with respect to testing. And what you can see here on the left side is a lot of weakness which we currently have. Attacks are increasingly remote, but at the same time, we see about 1/3 of the company have no established product cybersecurity program. 2/3 test not even half of the hardware and software. This is also an observation which we have. I mean, these numbers come from big surveys. You see the sources here below. But we see with our own customers that we have really this kind of imbalance of testing done where it's easy, where it's perceived easy, and at the same time not done where there's a lack of strategy. About half of the code have high vulnerabilities with static analysis. So this is obviously one topic which I will also cover in these 3 methods. And what we see on the right side is the industrial Internet of Things. Critical cybersecurity attacks, this grows exponentially and certainly will further on grow because we have more service orientation, we have more connectivity, and that means exposure is continuously growing. It's a major risk across industries. This is also why we thought to bring this experiences to this webinar series, because it's a technology demanding topic in terms of test and also in terms of cybersecurity, but at the same time it's also a high liability risk, which matters to all of us. Now, connectivity and also what we call ACEs, that is the evolution with respect to an increasing amount of automation of the convergence of enterprise and product IT, of ecology and of services. This is what these 4 letters of ACEs are about, means that the doors open for a wide range of attacks. That means independent what we face is with more standardization in terms of languages, in terms of APIs, in terms of service orientation. Standard tools for hacking will also be easier to use and are available. And that means there's a kind of a boost effect. With more connectivity, you will also have more security attacks. And that means from a very practical perspective today, cybersecurity is more interesting than drug trafficking. Now you can argue this is a good news because then drug trafficking might go down. I'm afraid that both are considered as very viable and sustainable sources of income. So we have to be alert on both of these topics. Now let's look into practical aspects of what ACEs means from a cybersecurity perspective. I take here a mobility example. We could take easily other example. Later on, I come with a case study for medical. So to balance the examples which we talk here in this webinar. In this picture, what we can see is different type of attack schemes. We have physical attacks. I mean, you could attack the system itself. You can also have remote attacks. That is possible with any sort of connectivity between a product, between a software system and the outside. These are growing. We see today an evolution which very fast moves into that a vast majority, 90+%, is done remotely. Only few would be direct physical attacks. This is typically this so-called proof of concept, this so-called approach to show that systems can be hacked, but a big amount of the vulnerabilities comes today from either phishing and or social engineering. And I say and or because in a way it's the same. Phishing is one type of social engineering, and we have to be alert that, as we say, the enemy is in our own bed. That means the scope of these attacks from inside the company, be it, let's say, inadvertently, which is the vast majority, or be it even by desire to, for instance, hurt your employee, that would grow, and this is growing very fast. And that means we will have, independent which industry and independent how this picture looks like, growing amount of these attacks from the outside. It means also from a product liability perspective, and that is often underestimated, cybersecurity has gained now the position of the key risk. If we go backwards 10, 15, 20 years, there were other risks with respect to product liability. But today it's cybersecurity for the simple reason that once a potential vulnerability is known in a highly distributed system, which is the Internet of Things, which is any sort of mobility service, any sort of other service, it will be exploited. And mostly by third party. See that in the statistics at the bottom, it's about 2/3 which are directly detected by a third party. And in most cases, once it's it will also be exploited. Now, what are the root causes? Because if you want to clean up here, we want to know why is it? And a major root cause is what we might call homemade processes rather than professional experience. Two examples here. A majority of project failure is due to a lack of systematic requirements engineering. You probably have heard about the chaos reports. That's about IT failures, and the number one reason aside insufficient process is typically directly requirements engineering. What is the impact of requirements engineering on security? Simply speaking, there is no direct connect from some security risk assessment, such as a threat analysis, into specific technical and functional requirements which are necessary to counteract this risk and therefore also improve on the specific vulnerabilities or mitigate this vulnerability risk by having security goals. Now, one can argue it's possible to do without explicit requirements, but as soon as we change software, these not so explicit requirements tend to be forgotten. And this is a real danger. It's a danger not only for cybersecurity, but since the topic is cybersecurity, I put this in the foreground. It's clear that this kind of omission of requirements could also have other consequences. But here, it's the risk that our security assessment would not trace into very hands-on technical and functional requirements. And 4 out of 5 cyber attacks happen due to not focusing on these security requirements. So we see the scope of the requirements is directly impacted. And there's one interesting study, which is why do we see it? It's often because misconfigured system. Not so big ratio is vulnerable code. User experience is a very big issue. And of course, there are also some other topics which come into the picture. So one takeaway is for the requirements, we need to be more efficient, more effective in identifying, in connecting them to the different security analysis and to keep this link from the security analysis to the security goal to the requirements and later on the implementation updated throughout the life cycle of this product. Now, speaking about traceability, let's look directly into a concrete example. And the practical application is here. When we look to this picture from requirements to design to V&V, we call this also triple peak for the simple reason that we have 3 major themes: requirement, design, V&V. And it's a peak that's this triangle shape, because we typically start at the top with the abstract and then move downwards to the more hands-on better understanding. And that means if we take a normal security analysis on the side of the requirement, we would understand market needs, we derived assets, that is what has to be protected. We do threat analysis if it is safety critical, like medical, mobility, etc. We would also have a HARA, that is a hazard analysis, which we need for functional safety. And we derive safety and security goals. So this is straightforward. It's defined by many standards and facilitates that we connect the risk with certain goals which mitigate the risk. If we go a little bit more into the implementation, then we derive product requirements, software requirements, and finally component requirements, which we use then to, for instance, pass on to suppliers or use in our own environment. From design perspective, it's a, let's say, very mirrored abstraction. We have a system level, which reflects the system understanding, the system analysis. We break that down into a functional model where you see different functionality which relate to each other with dependencies. And finally, we have the software hardware implementation, building blocks, depending on what kind of system you are working on. Now on the test side, and this is often neglected, we have the same sort of abstraction, and we need also And this is exactly what we call traceability, a connection from the left to the right. When we work on security requirements, we should also think in terms of how would that be tested, or vice versa. If there is a security goal or any asset which we want to protect, we should argue how can I specify a test case that would harm, that would mean that the system can be broken. In other words, these are what we call negative test cases. And just to be very pragmatic here, this is exactly what we call pen test. Penetration test takes this objective to penetrate a system, that is, identify negative requirements, coin them into test cases, show that a system can be penetrated. Now, this is the, let's say, good situation if we have penetration testers to do it. The practical situation is more that the penetration test is insufficient, and you would have external parties, so-called hackers, who are doing exactly the same thing. They look into what are the components, how is it most probably be designed, and then they get into the system. For that reason, we have here on the right side not only the topic of pen test. I come back on this word gray box, but we also have a robustness, fuzzing, etc. Anything in terms of test which helps to relate on the abstraction to this system analysis. Downwards to the implementation, these are the things which most of you know much better. We have functional test, interface test, integration test in the middle. That is where we glue components together. And on the individual component, we have what we call software quality analysis, SQA. That is static and dynamic analysis of the different units. Dynamic analysis is a unit test. Static analysis, for instance, a code analysis with some tools like PCLint, etc. All have their own relevance, and that means it's not one versus the other. We need all of them. And I come also back on that because it's a very key message in this webinar, that we are not here to say a certain penetration test is much better than a fuzzing or more effective than a unit test. We need a comprehensive test strategy which brings together these different methods into, let's call it, a set of methods which would be applied in the life cycle. And to be quite clear, if there's a redelivery, for instance, if you have an agile continuous delivery approach, or if you have DevOps in your product delivery, then you need certainly the respective security strategy to be running with each of these delivery. And that can be quite expensive if you want to do it thoroughly. And since we tend to reduce those things which are too expensive, what we see in many practical cases, especially in fast iterations of deliveries, there's a lot of unit tests, which you do in your Jenkins pipeline, which you do on your steady integration. But when we go to the higher levels, as soon as it cannot be automated, we face the gaps. And this is exactly this upper right level, but it's to some degree also static analysis, because static analysis is also something where you need human expertise. And I come for that reason back on this topic of static analysis. Now, with this triple peak analogy, let me just briefly show why this is an advantage for cybersecurity testing. And what we see here is a technique which is called test-driven requirements engineering. That means we connect test and requirements engineering already from the beginning onwards. Beginning means we are again on this top level here of these three different peaks. The peaks, again, the need, the solution, the product, or requirements, design, test. So we would start initially with requirements. I mean, normally when we think about requirements, we think about functionality. Security means, how can I corrupt this functionality? How can I get hold on assets? Now, one obvious asset is our code base, the software itself, data, services, code. If somebody can corrupt that, that's certainly dangerous, because then it doesn't anymore necessarily perform as it was specified. Other assets could include personal protected data, can include our IPR, which we don't want to get out of our company, etc. So we have to think now from an attacker perspective, what would be these assets and how can they be attacked? And that brings us into what we call negative requirements. That is, our system has to avoid, this is a negative requirement, that, for instance, a certain port can be used in order to make a denial of service attack. This is a specific negative requirement. The system must not get into a certain state. This is the basis of cybersecurity, that we coin such negative requirement in order to implement security goals. Now, TDRE has a big benefit, and this is this red line. It's not only going from left to right. That means we have a negative requirement, we make a test case. This is the forward approach from a tester perspective. Tester is here. He sees the requirements. He looks into how can we attack such a system, and then he creates test cases. Backwards would be the second advantage, is that later on, so we now are in a kind of a time shift when we actually test, we get results from the test execution. And this is still in-house. This is an advantage because the test specification that happens in parallel to the requirement, sooner or later you have a first internal delivery out of your continuous X pipeline or out of some agile incremental development, but you have a certain starting point which you test. And based on the test results, when you see we don't find defects, that's for a tester always quite ugly, because a tester wants to find defects, means we have to update. We might have to find new test cases. However, it can also happen that there would be some test cases which find actually a vulnerability. Then you give it backwards, because that gives us a new requirement, a new cybersecurity requirement. And this is why TDRE is so much helpful from a cybersecurity perspective, because it, on the one side, connects this abstraction long before the actual product is available. But when it is available, when there is agile increments, we would take this product in order to identify, was our security analysis sufficient, or was the tester sufficiently creative to find vulnerabilities, which means we have to update our security strategy. Now let's look into these three methods which I mentioned earlier. First one would be software quality analysis. That is, look at the lowest possible level. This is typically our unit development level, into static and dynamic analysis. Static analysis means we run some static analysis tool, such as PCLint, such as other code analysis tools, SonarCube, for instance, come into the picture, Clockwork, etc. And those would analyze many, many facets of how code can be, let's say, improved. Now, the challenge with the static analysis is that you need to tailor these checks very carefully, because otherwise you get just an overwhelming amount of, let's call it, warnings. And we don't like warnings. I mean, you know that from your own compile expertise, a warning is annoying. So what happens in most of these cases is that the amount of static analysis is reduced because the people drown in warnings. What we recommend is the opposite. We recommend that you really connect the analysis, the checks, towards what type of vulnerabilities you want to find. And based on this analysis, you really get only a subset of the warnings which are relevant. And you find example here, for instance, that you would have in a C, some language, some passing of parameters into procedures, some pointers which can point to a wrong direction. For all programming languages, equally relevant would be variables, the ranges, the type. So you know that this can be a quite a difficult situation if you have type violations. Can also be accidental overriding. This is a typical attack scheme that you try to override memory with malicious code, typically code which would sooner or later be executed. And finally, you can also make analysis based on what would be behaviors in case of inputs, in case of, let's call it communication paths in the software, which are misused. So this is typically the misuse cases at the interfaces, abuse cases of the software or its components, but also user experience. This is what we call the confuse cases, because that also can lead into some malicious code, even if it was just happening because somebody inadvertently left some port open. And this is, by the way, a very critical topic, because most systems during their development keep all sort of debug information. And if that is not carefully removed, and we see that again and again in our independent software quality analysis, that such, let's call it backdoors in terms of development support would be accidentally left open. And that is then, of course, also an entry path for future hacker as soon as the software is out there. Now, some people argue it's password protected, but in most cases, these passwords are not strong. And this again brings us back into security attacks, where we should never argue that it takes a long time to test all sort of, or to check all sort of combinations which are feasible. We have today very powerful tools for password cracking, which can be used here. And maybe down the road, if we go into quantum computing, we will have completely new ways to generate such, or to crack passwords. Second relevant methods is brute force, but intelligent brute force fuzz testing. Fuzzing means that we take a more randomized scope, not completely black box, not completely random, because that would be too expensive. So what is done in fuzzing is we take information about what would be data ranges. We go to the boundaries, what would be specific interfaces which can be maybe overloaded with denial of service, etc. And then we would send messages to these different interfaces, to these different ports, and try to find out what would be the respective reaction of the system. Is it going to detect it with an intrusion detection system? What would be then the behavior of the system? Or can also be that if it's not detected, that there is at least some sort of response that is a robust system. But if it is neither nor, maybe you can also use such, for instance, a buffer overflow, which is one of the standard approaches in fuzz testing, in order to position malicious code into the system. Third methods, which I want to illustrate, I spoke about 3 powerful methods. That would be pen testing. Now, pen testing has also very rich content from testing on the interfaces to network analysis, network penetration, and also the software penetration. So you see also here different type of abstraction, which could be used from the outside or from the inside, but generally with a product, you can do that rather early if you have a continuous development, continuous delivery model. Any sort of internal delivery could be passing fuzz test and pen test with some automation. Now let's look into how we really benefit from that and what the method looks like in practice. I use here a kind of what we call a V abstraction, V because it's a V shape. We put the different abstraction levels from top down which is again what we have seen earlier in this triple P analogy, that we go from the requirement into the component and finally to the architecture design and coding. So this is the abstraction on the left side for creating the product, and on the right side for verifying and validating. Verification would be down here, where you still look into the software. Validation is the upper half, if you want to put it as a half, which is we look more from the outside. Both is necessary. I mentioned that already. It's not either or, it's more to combine it. And we've created 10 steps just to give some sort of cookbook recipe, which briefly explained mean first is a sort of a reconnaissance. That means understanding with all means which are available what this system is built upon. Clearly, if we have here the attacker perspective, so we are not going to use design information which is not disclosed, but we use all sort of external information which would be accessible also for a hacker. Reconnaissance helps us to get an understanding of what's inside the software system. Then we analyze that in a structured way in order to identify what could be assets. The typical assets I mentioned already, that could be the software, which is IPR, it can be data, which can be personalized. These things you want to make sure would not be abused. With the asset, we can start to make the so-called TARA, that's the threat analysis and risk analysis, which allows us to understand priorities. I mean, sometimes you will find threats which look interesting, but which are really hard to achieve. And so we put them on a lower risk level. With that finished TARA, we take the top ranking threats and identify what would be the security goals which are derived from these top ranking threats. Then we move over to the right side, which is the real testing. So we make testing. Typically, we call it a minimum viable penetration test in order to not make it exhaustive. We look into how this behaves. We use KPI indicators, which would highlight areas which can be rather easily attacked. And finally, once this underlying software would be improved, we would need a regression testing. And again, this regression testing has to comprise security and therefore also needs to be part of our overall test strategy. Now, one thing more would be that we now look into what are typical results. So initially, the typical result would be that we understand the usage, the misuse cases. Then we look into what is available in terms of how would I design such a system. That has already a lot. Then we make certain error models, which we apply in order to identify what kind of let's say threats would already be possible with today's software. For completeness, I also include here TDD, which is test-driven development, because it's a classic agile development technique, and it relates to this TDRE, not only because it's test-driven, but also it's a technique where you start with a unit test case and then you develop the software which fulfills the unit test case. This is certainly the very single best test approach. We rarely do that on a system level, could be done the same way, but on the entry level, we should certainly do that. On that basis, we apply the TDRE. These are these horizontal lines. Remember, we're forward and backwards. And we would then take the KPI to identify, for instance, what is our threat coverage, the security and efficiency, etc. Let's look into a hands-on example, which is coming from medical. It's an insulin pump, which is used for people with diabetes to control the blood sugar. Typically, there's a sensor. It's a kind of a control loop. The sensor measures on the blood. And if there's not enough sugar, you would get sugar. If it's too much, then you would get specific medical support automatically. Now, this devices have one obvious immediate safety risk, which is that this insulin is, if you get too much, life-threatening. That means you don't want to have this device being manipulated. And that is why we were looking into it, because it helps to talk about something which everybody understands. And we can then also see how would be typical attack schemes. Now, you can imagine these systems which are typically approved by FDA will not have all their content publicly available. That was another reason why we use it here, because it's very similar to other professional systems, be it robots, be it finance systems, etc., where there's also no explicit specification available at the outside. However, what we can do is we can guess, we can make informed guesses, we can make literature research. We could ask ourselves as experts, how would I design such a system? Because the block diagrams, this is known. In other words, they are typically always the same sort of weakness, one being standardized interfaces. Another one would be that you don't achieve a complete handling of all the critical requirements. And in consequence, there are different vulnerabilities to be tested. So what you do is we take these 10 steps, which I've shown before, and we would then look into how can we practically use it. That is, first of all, as a hacker, as a, let's call it white hat, as a friendly hacker, we always try to first find out what would be our attack scheme, what kind of information is available, what would be architecture, which is used here, maybe also improved. And then we identify different type of test case. Remember, I was talking about the static analysis, first method. Second method, the integration. And thirdly, which is, for instance, fuzzing. And then on the system level, the gray box penetration test. Gray box penetration test means that we take as much as possible known information, such as what components, what are their vulnerabilities, or whatever we know, which is publicly available, or at least in sort of what we call gray areas in the darknet. What is available can be used, because a hacker would also use it. And in order to then also instrument the quality of this test, we will also use error seeding. That means we build into the system several errors, and then we can easily identify the effectiveness of our security test by identifying how many of these seeded errors, which are unknown to the test team, are actually detected. And that is a quite nice approach, statistically speaking, because we not only improve the amount of test cases to focus, because we know about what vulnerability to test, but also we reduce that kind of navigating in the fog, because with the seeding, we can, for instance, identify which type of defects would be detected with the current test strategy. And that means if we now compare this independent V&V, which we typically doing, means traditional approach, you need more effort, but you find less security risk. Why? Because on the one side, we combine many methods, so that adds to the effort, but at the same time also understand that not everything is already sufficiently available, and that means we have here waste of effort, which in this gray box testing, gray because we utilize any wide available information like components, code, etc., and at the same time also make sure that we operate as a friendly attacker. We don't want to do it completely white box. It's possible in theory, you can re-engineer software components, but as I said in the intro, this risk is not anymore as high as it used to be. To conclude, let us look into how these different methods really provide benefit, and we see this strong effect depends really. Each method has their own areas where there's a benefit. Manual reviews, even if they're expensive, are extremely important at the early stages, like requirements errors, while static code analysis obviously applies fully to code and should not be used beyond that. Of course, you can include it into your DevOps pipeline or DevSecOps pipeline, but still it's relevant to be clear that we have different test techniques with their different benefits, which have to be identified and part of our test strategy. So the major takeaway here is to combine these different methods, use KPI as a kind of feedback instrument on these typical objectives of effectiveness and efficiency. Now, often we would be asked, can you coach us in doing this static analysis, fuzzing, pen test? And I will tell, in principle, yes, and we do that, especially when it comes to static analysis, because that's real help, a big support. On the other side, we also have to be careful because any sort of homemade solution always has the two disadvantages, which is on the one side, could be a solution which is incomplete. That means we will have gaps afterwards. And second, also that this homemade solution is just not delivering. It's maybe too hands-on. And therefore, we have to balance these two perspectives, and that's exactly also what this cartoon is about. Unfortunately, that this encryption code, and this is the reason why the cartoon is not perfect, and that's why it is written. Now, coming to the end, there's of course much more information available from our security test experiences, also tools, etc., standards. And if you have some time, we can still further discuss if you send me some mail afterwards and you get more recommendation. But for now, it's important that you train people. And this is an evolution which we currently see a lot. You remember, we talk about competences, and the lack of competence means that we have to educate. And since we have here a capacity problem, we have to intensify the quality of our training. And this is why trainings get more and more relevant, especially in security, this security type of internal trainings, which would be mandatory once per year as an e-learning. This is a trend which we see with many customers. We help them on such training preparation. For those who want to see more about this convergence of enterprise and product IT, I invite you to our Vector Forum, which is in May and June on a weekly basis, 1 hour with Q&A. And it's 1 o'clock in Europe time, morning in Eastern time, and evening in Asia, so that for different groups it should be accessible. That is the status of what I want to get across with these 3 powerful techniques: static analysis, fuzzing as a brute force method with intelligent approach, and gray box pen test. I talked about the challenges which we have with cybersecurity and also the product liability topic, because this is why we all are here in a situation where we have to show and demonstrate that we follow the state of the practice, which is standards, release standards. And therefore also my recommendation, document what you're doing. If you run security tests, also make sure that you have reports afterwards available. Finally, I was showing practical guidance from this medical case study where we apply these different techniques with a focus on the pen test, because often the classic black box approach to pen test is still maintained. But this example very clearly showed that black box pen test has low efficiency because of the brute force character. You need a lot of test cases to find something, and also low efficiency. And these two, effectiveness and efficiency, have to be cured. And this is what we wanted to show with this case study on this medical insulin pump. That being said, I thank you very much for the listening, and I hand back over to Susan for the Q&A session.
We did have a question. In a large network of systems interworking, does PEN test or pen test make sense for the system which is not exposed to end users? If yes, then what kind of tests have been planned as part of pen tests?
Okay, so penetration test today is used for very different systems, and there's exposure to end users. That's a good point. I hear that quite often. I tried to explain, but I will again put it different words, why this end user is not the only risk which we have this with IT and software system, namely because an increasing amount of attacks happens from the inside. And that means inside can be really anything. Give you two examples, which is not a direct end user exposure. The one would be that malicious code or data is produced or created during the initial development and placed into your software. One might argue this will not happen in my company. I wish it was like that, but we see, and I mentioned this word of social engineering, that these things increasingly happen. Again, typically not deliberately, but much more because somebody would get into either the direct development, or at least is able to send some sort of phishing approach to a developer. And I'm sure all of you receive such emails. You click on a link, and you would get some software maybe very silently placed into your PC, into your workstation, into your environment where you develop code. And at a given moment, it would do exactly the same as you would do as an external port. It would create a copy of some malicious code and just position somewhere in a memory space, assuming if this is done quite frequently, or if some code would be manipulated to point towards an external interface that can be exploited later on. This is one reason that we would not even need an end user. We can take any IT system, be it embedded or be it hosted or be it in a cloud service, where this strategy is increasingly used. The second one, which we see also quite frequently, is now ransomware, which is used to lock certain parts of software. Again, it's not even mandatory to lock the complete system, which looks then quite obvious, but you can also lock certain functionality. You can corrupt certain functionality that it doesn't work correctly. And later on, when this is in the field, you can use or misuse this ransomware in terms of demanding some sort of compensation. In other words, true that penetration test has been created from this external user perspective, but today we as independent pen testers use it more and more also to identify what could be mechanisms to infiltrate a system from the inside.
First off, thank you so much for presenting with us.
Thank you. And if you have questions, send me the mail. And thanks, Susan, for the hosting.